Good day, everyone. This is a Salt Vine robot. Our team members include Juan, Mohammed, and myself, Abdul Malik, who are all majoring in electrical engineering. And we have Kevin as well, who's majoring in computer engineering. Our project includes building a soft vine robot that can navigate through tight spaces. We plan on using pneumatics to control how the robot moves. We will also be having both manual and autonomous mode. The reason behind this project included being able to make a device that can navigate through hard to reach places. And this can have numerous applications, such as in the medical field, being able to retrieve small objects within someone's body system, being able to retrieve certain active artifacts during excavation sites in archaeology, and also being able to help victims of natural disasters such as earthquake and provide instant relief. Our project constraints are mostly economic and environmental, time and educational, and safety. With economic and environmental, it is hard for us to provide all the funds for this project, being college students. And also with the pandemic, it has also created a constraint on logistical issues. And then with time and educational, it is hard for us to devote as much time as we would initially thought because we have other responsibilities as well with classes and jobs and internships. And then educational being the fact that we're still naive in how deep this field is, and we're constantly trying to learn as we go on. And then safety-wise, with soldering components, that could be a huge safety risk because we're dealing with high temperature. And also with the pneumatics, we're also dealing with high pressures, and we could also risk other parts exploding depending on how we choose to manage the pressure. Our goals and objectives, just to reiterate, is to design a robot that can navigate through tight spaces. We'll be using both manual and autonomous mode to help the robot navigate through the maze or the obstacle course. And for our stretch goals, we'll be using a gripper system that can easily retrieve objects at the end of the course. And also in the autonomous mode, we plan to use CV or computer vision to program the way the robot moves through the obstacle course. Our project specifications are lined up as you see. We have our robot body, which would be of length 10 feet and 5-inch in diameter. Our lead acid battery will have ratings of 12 volts and 5 AH. And our camera lens will have a focal length of 2.1 millimeters, FOV of 155 degrees. And our gripper radius should have 4 inches, body growth rate of 2 inches per second, and air pressure flow shall have 5 pounds per square inch and 10 cubic feet per minute. And here's a more simplified version of our division of labor. We each have a primary role to play, and some of us have secondary roles as well, depending on how heavy the workload would be in the coming months.
So this is our block diagram. Starting from the top left in yellow is our power subsystem. Then in red is our camera and video processing subsystem. Then in gray is our motors. In blue is our pneumatic subsystem. In white is our custom PCB control board. In orange is our robot controller. And in green are our sensors, not including the camera. Moving on to the mechanical design, the robot body is the part of the robot that is going to be lengthening and retracting. Then the artificial muscles or SPAMs are going to be lining the diameter of the robot body and are actually going to steer the robot in any direction that we want in 2D space. The robot base is what houses the undeployed part of the robot, and it also serves as a pressure chamber for the robot body. The internal rollers are at the tip of the robot body, and they aid the robot in retracting onto itself. The tip-mounted cap is actually part of the same assembly as the internal roller and serves as a solid surface for us to mount our sensors and effectors. And the pneumatic controls are the part of the robot that controls all the pneumatic actuators. The body is made out of LDPE poly tubing. This is very thin plastic that has a low bursting pressure of 3.2 psi. Over on the right, you see an image, an illustration of how eversion works. Basically, when we pressurize the robot body, it will lengthen by inverting itself. The pressure that we need in order for the robot to lengthen is about 1 psi, which is good because our max bursting psi is about 3. When we were picking the material for the robot body, we needed something that was flexible but not stretchable, so that it would not change size from one deployment to the next when it's pressurized. We could have gone with LDPE polytubing or TPU coated nylon fabric, which is similar to the fabric that backpacks are made out of. The problem with the fabric is that it is about 4 times more expensive than the LDPE tubing, and it also doesn't come in tubular form, so we would have to sew it and heat seal it in order to create a tube, and that's why we went with LDPE polytubing. The artificial muscles, or SPAMs, which stands for Series Pneumatic Artificial Muscles. They are the part of the robot that actually steers the body. Whenever you pressurize a tube, it actually shortens in length by a small amount. And by putting rubber O-rings down this tube, you can actually accentuate just the characteristic and make it more pronounced, so that when you inflate it, it actually contracts by a lot more length. And by putting these in all the way around the robot, we can actually steer the robot in any direction we want. More about the base. The base is, if you can see this air inlet right here, that's actually what's going to pressurize the base. And inside the base is a spool and a motor. So when we want to lengthen the robot, we will pressurize this base and we will spin the spool so that we can give the robot more material for it to lengthen. Then when we want to retract, we spin the spool in the opposite direction and sync it with the internal rollers at the tip of the robot for it to retract. The cap is the most intricate part of this entire robot as far as mechanical design goes. It has to be attached to the robot, but it also has to be able to slide up and down the material. So in order to attach it, but not permanently, we use magnets and ball bearings. And inside this cap is actually the internal rollers, which you can see here. The internal rollers are coated with this high friction material that is used for us to be able to grab onto it and push the robot material back onto itself. Moving on to the pneumatic portion, there are several pneumatic components, starting with the portable air compressor, which holds all the potential energy for our pneumatics. Then we have pressure regulators to control what pressure we are at, followed by check valves, which make sure that the pressure is only going in one direction. And then we have solenoid valves, which can be switched from injecting air to releasing air from the robot body and air muscles. And then we have pressure transducers on those pneumatic actuators so that we can measure how much pressure is in each one. Finally, we designed a couple obstacle courses. We're going to be making the obstacle courses out of plywood, and the obstacles are actually going to be made out of styrofoam. We're going to be using Velcro to attach these obstacles wherever we want so that we can rapidly change the orientation of anything.
So for the hardware, we have an ATmega MCU that's being used to control the 3 motors along with the gripper motor, and we're also using that to control the pneumatics. We're also going to be feeding the sensor data into the microcontroller, which is going to be sent to the Raspberry Pi. And the hardware also includes a joystick and a few buttons that would allow us to control the pneumatics and motors manually. So when picking our microcontroller, we were deciding between the ATmega 328, the 2560, and the Raspberry Pi. We decided to go with the 2560 as it gives us ample digital and analog inputs, and also has enough PWM outputs for the motors that we have. It also supports I2C, SPI, and UART. We're going to be using I2C and UART. So here's the schematic for our microcontroller using the ATmega 2560. We added an ICSC programming interface, which is going to allow us to program the MCU after it's been soldered on the PCB. We also added LEDs for power and serial communication. We also have a reset switch, bypass capacitors, headers for digital and analog pins. We also added a USB serial interface using the CH340G chip that allows us to interface with any other serial device. We're going to be using this to send sensor data to the Raspberry Pi via micro USB. So for the motors, we'll be using a 12-volt square phase gear motor that's going to be placed at the base and will be used to drive the spool. And we'll also be using 2 metal gear motors for the roller motors, as seen over here. Those will be placed at the tip of the worm and will help with retraction and growth. We also have an SG90 servo motor that's going to be used as the gripper of the robot, so that will assist with gripping items And to drive the two gear motors and the square face gear motor, we'll be using an L293 motor driver along with motor encoders for all the motors. So this showcases the motor schematic with the L293 drivers. We're using 3 PWM inputs here because we have 3 motors that need to be driven, and the output of all these motor drivers go to this header over here, and this will connect to the 3 motors. We also have decided to use interrupt pins 10 and 19 to be used to interface with the encoders. So here's an overall block diagram of all of our motors. So we have the MCU here, and that's going to be used to send the PWM to the motor drivers. For the SG90 servo, we're going to have that connected to a digital pin along with the 5V and ground straight to the MCU. We'll also be incorporating a motor control switch that's going to let us switch the position of the spool motor. So for our altitude sensor, we'll be going with the MPL3115A2, and it's going to be sending data to the ATmega2560 over I2C. The MCU is going to be writing serial data to the Raspberry Pi, which is going to include the sensor values, and that will be displayed on the user interface as seen over here. And the sensor is going to be placed on the worm cap, so all the readings will be coming from the tip of the worm. So as it expands and navigates, it'll be sending back all that data. And to be able to use that sensor, we had to design a logic level conversion circuit, as the altitude sensor is a 3.3 volt device and the ATmega2560 is a 5 volt device. So we used the BSS138 N-channel transistor, which allows us to convert that 3 volt 3 signal coming from the sensor to a 5 volt signal. So on our PCB we have a header, the 3 volt 3, power and ground, and the SCL and SDA, and that would be used to connect to the sensor. For the autonomous navigation, we're going to be using phototransistors and a USB camera. The phototransistors will be placed on the worm cap. We're planning on using 6, and that would allow us to read light data and help us navigate which way that we need to go based on how much light is being measured. And we'll be using a USB camera to be able to follow the specific color of the light using OpenCV. So both of these would be used to help with the autonomous navigation and light following. As was mentioned previously, we'll be using pneumatics to be able to inflate and deflate the tubes, and we want to be able to control these with the microcontroller. So we designed a 12 volt control circuit with a TIP120 Darlington transistor and a general purpose diode. So this circuit is basically used to control the output of the current to the pneumatics.
For our main power source, we'll be using a battery, and we researched different types of batteries that will be appropriate for this project. And we ended up with 2 main batteries, the precision lead acid battery and the LiPo battery. After a detailed comparison, we decided to go with the lead acid battery because it's much cheaper, provides a higher amp hour rating, and the chargers are also very cheap. Here's a simplified version of our power design. We plan to use our battery charger of 12 volts 4 amp to charge our battery, which would be 12 volts and 5 AH rating. We also plan to use 2 buck converters, which would reduce or step down the voltage to power Raspberry Pi and altitude sensor. And here's a more intricate design of our power conversion. We plan to use our 12 volt battery to power motors and pneumatics, our 5 volts, which would be stepped down using a power converter to power the MCU, and our 3.3 volts, which will also be stepped down as well, to power the altitude sensor.
So this is the overall PCB schematic. It includes all the schematics that were discussed previously. And this is our PCB board layout, which was designed in Altium. The left side is the top layer and the right side is the bottom layer. Here's a 3D CAD model view of the PCB. There's a power jack. You also have a micro USB connection here. So to be able to manually control a robot, we decided to go with getting a joystick shield for the microcontroller that already has the joystick and the buttons. and we're going to wire that directly to the analog and digital headers of the PCB. This was a lot more cost effective than buying an Xbox controller or designing one ourselves.
The components. It also allows the user interaction and for the user to get some feedback from the sensors. It also handles the computer vision aspect of the autonomous navigation in this project. Here on the right, we can see the overall diagram of how the user Raspberry Pi PCB and hardware components will interact all with each other. For the user interface, we're going to implement a user PyQt, the Python framework. It presents the user with some live feedback from all the sensors, as well, so some feedback from the camera so the user can navigate space. As well, it allows this mode switching between manual and autonomous mode. Here on the right, we can see our first sketch of what the user interface should be looking like by the end of the project. So we have the manual and autonomous mode. For the manual mode, we're going to have a joystick controller that sends signals to PCB board, which controls pneumatics as well as the motors. It also has a sensor interact with the Raspberry Pi to report information back to the UI. And we can see that all here represented in the diagram on the right, where we have the components, the PCB, Raspberry Pi, as well as the hardware and the user. For the autonomous mode, the Raspberry Pi will handle most of the CV computation. The PCB gets the growth signals from the algorithm outputted by the computer vision and controls the motors and pneumatics. Some of the sensors in the camera will just send feedback back to the UI, and we can see that over here in the diagram on the right as well. For the computer vision, we have chosen to go with the CSRT tracking model. This is a model that trains correlation filters with compressed features. It's a little bit slower than the KFC algorithm, but it's very robust to unpredictable motion, which is something that we have to consider given our project specifications. It also recovers from failures, not including failure from total object occlusion, but it's not something that we should worry for this project. Computer vision will be handled using OpenCV, which is a library that focuses on image processing, video capturing, analyzing, and including face detection as well as object detection. It's an open source cross-platform library that provides tools for any kind of image and video processing. Some important modules that we're going to be using in this project is going to be IMG Prod, video.video.io, as well as IMG Code CS. The object tracking itself will be implemented by using a frame-related grid that allows the tracking algorithm to determine which way the robot should move, and so the object is centered and reachable at all times. And here on the right, we can see how we have the horizontal and vertical axis and how the robot should be steered depending on where the object is located. For the sensor signal transmission, the sensor data will be received and transmitted among the PCBs via I2C. Transmission data will be transferred among all PCBs all the way to the UI. Controller signals will be received by the main PCB and used for motor and pneumatic control. And here on the right, we can see how the transmission and the controller class will interact with each other, as well with the sensors and the PCB. For testing, the motor testing we're going to use in the Mega 2560 for prototyping, as well as the L293 motor driver to control motors. The pneumatic testing is going to be done mostly with the breadboard prototyping as well, using the Mega 2560 and the TIP120 transistor to control those pneumatics. Something else that we have to test in the pneumatics is the airtight seal of the base, to make sure no air escaping while inflating. So mechanical testing, we're going to have to test the retraction and spool synchronization, as well as the gripper servo tactile strength. For the software testing, it's going to be mostly just the image processing using the camera, as well as the UI testing using PyAuto GUI. And for sensor testing, we're going to test our altitude, pressure, and photo transistors with the Mega 2560 as well. The budget for this project comes out to be around $1795.62. Here we have a breakdown of the bill of materials for the main components, as well as the ones that we haven't purchased as well. This is our timeline of the project up until the midterm demo. As you guys can see, we have divided the work almost evenly. We are working mostly on separate things up until all the parts have been delivered, so we can start with the integration part of the project, which brings me to our progress. So the progress design as well as electrical design are almost complete. Power design is totally complete, and the software design is the one that's underway, and we will need some work once all the materials are done and the project is completely integrated, which is also 20%, which brings us to an overall of 65%. Some successes that we have had so far is that we have a significant PCB design complete, some STL files are ready to print, laser cutter files are ready to be cut, but we're waiting on acrylic order, and we have decided to go with a pre-made joystick in order to save some time and money. When it comes to difficulties, we have the LiPo battery was expensive, so we found an alternative. managing opportunity cost of some features, as well as the pneumatic design, which is largely untested at the moment and might require increasing budgeting.